Okay, so now we come to chapter 6, probability. So the learning objectives are to understand 3 laws of probability. So you might ask the question, why do we want to talk about probability in a research methods course? And the reason is because probability is the language of statistics. So in order to use statistics, we first need to understand the basics of the language. We don't need to go down into great mathematical detail, but at least to understand the core principles. And as we'll see, they all turn out to be useful when we start talking about statistics. So what exactly is probability? So that seems trivial, right? Probability is just chance. It's the chance that something will happen. What does the chance that something will happen actually mean? It means the long run relative frequency. So relative frequency means the proportion of times that something occurs. Long run means over a very large number of experiments. So if we, for example, are tossing a coin, if we toss a coin a very large number of times, the proportion of times we get heads or tails should be very close to the probability of getting a head or a tail if you toss that coin. So, if the coin is fair, what we mean by fair is generally that heads and tails are equally likely. So clearly after a large number of tosses, the relative frequency should be both close to a half, right? A half for heads and of course then a half for tails as well. And the notation we're going to use in this chapter and in the rest of the book, PR is short for probability, and what we put inside the brackets is the outcome. So here I've used H as short for head when we're tossing a coin. So although in this course I've presented it as statistical formula being largely irrelevant, the language, as I said, is important and some knowledge is helpful. And indeed, we can show that anybody who gambles or invests should really know the basics of probability. If you fail to follow the rules of probability, that guarantees that you will lose on average when gambling or competing with someone who knows how to follow the rules. So what are these rules that help us to work out the chances for combinations of outcomes? So we're going to start with a set of outcomes which are mutually exclusive and exhaustive. So you remember that means exclusive means they're unique, right? You can only have one of them. Exhaustive means it covers all the possible outcomes. So for example, if we toss a coin, in theory there are only 2 possible outcomes, head or tail. Is that really true? Well, normally in class at this point, I would do a little experiment to show you that it's not necessarily quite that simple. So if we take a Hong Kong dollar $5 coin, there is actually a third possibility. So what's the third possibility? Well, the third possibility is that it lands on its edge. So a $5 coin has a very thick edge. So in theory, you could have a $5 coin that landed on its edge. Of course, in practice, it's almost always going to fall over to become either a head or a tail. So these are mathematical simplifications of reality, right? So we're assuming that when we toss a coin, we only have 2 possible outcomes. And this set of outcomes is what we call the sample space. Now, to start out with, obviously all probabilities must be in the range between 0 and 1. Why? Because they're relative frequencies. So obviously, the frequency can never be less than 0, and a relative frequency can never be greater than 1, because a relative frequency with 1 would mean it occurs all the time, right? So that's the maximum value is 1. Okay, so now we come to our first law of probability, is when to add probabilities. So the probabilities of mutually exclusive outcomes add. So this should also be obvious in terms of relative frequencies. So in this case, obviously the probability of a head plus the probability of a tail must add up to 1 if heads and tails are the only 2 possible outcomes. Right? So that's obvious. So that's why for a fair coin, the probability of head and tail must be a half, because by a fair coin we mean probability of head equals probability of tail. and so they must both be a half. So that's the first law of probability. Now, what about multiplication? So for independent events, it says probabilities multiply. So what are independent events? So we used the word independent before in terms of independent and dependent variables. But the meaning of independent here is quite different. Here, by independent events, we mean they have no influence on each other. So if we toss a coin twice independently and there is an equal chance of head each time, this is what we call a repeatable experiment, then the probability of getting 2 heads is just the probability of a head in the first toss times the probability of a head in the second toss. And if the chances are equal, then we don't need to distinguish between them. So the probability of 2 heads is just the probability of a head squared. So for this double experiment of a double toss, there are of course 4 possible outcomes: head head, head tail, tail head, and tail tail. And of course those 4 outcomes, if we add them up together, they must again add up to 1, because we must get one of these 4 outcomes. So this is quite simple, except usually we don't really care about the sequence of the outcomes. So we normally would just care how many heads did we get in our double experiment. So we can get 0, 1, or 2 heads. So the probability of 2 heads is just the probability of head head, which we said was the probability of head squared. So if we use p to be the chance of a head, then the probability of 2 heads is just p squared. The probability of 1 head is the probability of head tail or tail head. And again, these are mutually exclusive, so we can add them together. So we get twice p1 minus p, because if p is the chance of a head, 1 minus p is the chance of a tail. And similarly, the probability of no heads is the probability of getting a tail twice. So it's the probability of a tail squared, so it's 1 minus p squared. So this case is relatively simple, but in general we need to work out the number of combinations. So for example, if we toss a coin 10 times, what is the chance of 9 heads and 1 tail? So then we would need to be able to work out the number of different ways this can happen. And it turns out there are 10 different ways, because the tail could occur in any one of the 10 tosses. So what we end up with is 10 ways. So that's easy. So that's just 10 times the probability of 9 heads times the probability of a tail. A little harder now would be 8 heads and 2 tails. So now the number of ways is there's 10 different tosses on which the first tail could occur, another 9 different places where the second tail could occur, but we don't care about the order. So there's actually 45 different ways of getting 8 heads and 2 tails. So we can write this mathematically as 10c2, which is the number of combinations of getting 2 ways out of 10. So we write that as 10 factorial divided by 8 factorial times 2 factorial. So 10 factorial is the number of different possible sequences of 10 items, which is 10 times 9 times 8 all the way down to 1. And of course 8 factorial is the number of different possible sequences of 8 heads, and 2 factorial is the number of different possible sequences of 2 tails. So then we get the probability of 10 heads is p to the 10. Probability of 9 heads is 10 times p to the 9, 1 minus p. Probability of 8 heads is 45, which is 10 times 9 over 2, p to the 8, 1 minus p squared, and so on. But we don't need to know these formulas. We can use tables or a calculator or a computer. But what we've just done now is what we call the binomial distribution. So this set of probabilities is very important in statistics, and the usual notation is capital B for binomial, n, where n is the number of trials or tosses, and p, where P is the chance of success. So what does success mean? Well, I can define success as either a head or a tail. It doesn't really matter. So I can work out all the probabilities if I know that this is a binomial distribution with n trials and a chance P of success in any one trial. And we'll see later on we can use the binomial distribution to check if a coin indeed might be fair or not. Okay, so the third element, the third law, we first of all need to introduce another concept. This concept is conditional probability. So conditional probability is that we want to calculate the chance of an event A if we already know that some other event occurred. So if we know an event B occurred, what then is the chance of the event A? So obviously if A and B are independent, that means that the chance of A occurring has nothing to do with the chance that B occurred. So we're generally interested in this when A and B are not independent. So let's think of an example. So if I tossed a coin 5 times and you happen to see that the last toss was a head, how should that affect your estimate of how likely it was that I got all 5 heads in 5 tosses? So first of all, we have to work out how to write this down. So we use a vertical bar to mean conditional on something. So this is the probability of head, 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 head. So that's the probability of 5 heads, conditional on the last toss is a head. So this one actually is rather obvious. This is clearly just going to be the probability that the first 4 are all heads. But we can solve this using a rule known as Bayes' law. So this is our third law of probability. So why is it called Bayes' law? Well, there is actually apparently a law which says most situations where a law is called after someone, they're not really the one who came up with the idea. So Bayes in this case is Thomas Bayes, who was a minister, not a minister in the government, a minister in the Anglican Church in the 18th century, and he came up with this formulation. So if you're French or German, you believe that Pascal or Gauss actually came up with this law, but Bayes was the one who formulated it in words first, arguably. So Bayes' law tells us that the probability of A given B is the probability of A and B divided by the probability of B. Right? Or we can write this the other way around. It's the probability of B given A times the probability of A divided by the probability of B. So the easiest way to remember this is to just think the probability that A and B occur is the probability that B occurs and then A occurs given B, but it's also the probability that A occurs and then the probability of B occurring given A. In other words, it doesn't matter which order we find out. We're trying to say we can think of it as a two-stage problem. We first find out whether A occurred and then the chance of B occurring given A, or we first find out the probability that B occurs and then the probability that A occurs given B. So obviously if A and B are independent, the probability of A given B is just the probability of A, because B has nothing to do with A. So in the case A and B are independent, we get the probability of A and B is just the probability of A times the probability of B. Okay, so how is that going to help us in this situation? Our example was the probability of 5 heads given the last is a head. So the probability of the two things together is still the probability of 5 heads divided by the probability of B. So that's the probability the last one is a head. So that's just P to the 5 divided by P, which is P to the 4. So this one is obvious. So this one is not, we don't really need Bayes' law. We can work it out. So the important thing for this course is simply to understand the idea of conditional probability and know about Bayes' law. We don't need to memorize it. So when might this be useful? Well, if, for example, you play cards, Bayes' law is very useful. So whether you play bridge or poker or blackjack, any of these games, You're essentially working out the chance of a set of outcomes given you have some partial information. So for example, let's say I have a pack of well shuffled cards and the first card I deal is an ace. What is the chance that the second card is also an ace if I use the same pack without shuffling? So the probability that the second card is an ace, I'll call it A2. The probability the first card is an ace, I'll call A1. So what's the probability of A2 and A1? That's 4 over 52. There are 4 aces there to start with out of 52 cards. And then A1 is 4 over 52. A2 as well would then be 3 over 51 because there are 3 aces left out of 51 cards. And then the probability of A1, as we've already said, is 4 over 52. So the probability of A2 given A1 is just 3 over 51. Now notice that compares with if we reshuffle the pack after dealing the first card, we would get 4 over 52. Right, so we've got, the whole point is if we don't reshuffle in between, we've got 1 less ace in the pack and we've also got 1 less card in the pack. Right, so assuming it's still by chance. So clearly in these sorts of situations, we can use Bayes' law to help us work out the conditional probabilities. Oh, so yes, so there are interesting stories behind this. So some of you may have seen a movie. I think there are at least 2 movies about university students in America going gambling and playing blackjack usually and managing to make quite large sums of money until they get thrown out of the casino. So how does this work? Well, if you're playing blackjack, the idea of blackjack is you trying to get as close as possible to 21 points in your cards, but not getting more than 21 points. So you have to understand how to count the points in a card hand in blackjack. So in blackjack, for all the cards with numbers on them, the value is the number. For the Jack, Queen, King, they all have a value of 10. And then the special card is the ace. So the ace in blackjack, you can choose to either make it worth 11 or worth 1. So to get 21, an ace plus any of 10 Jack, Queen, King, those 2 cards together would give you 21 exactly. So 21 is obviously the perfect score. But if, for example, you got 2 aces in a row, you could consider that to be 12 points or 2 points, right? And then you could continue to draw cards. But if you draw another card and you get too many points, then obviously you have lost. Okay? So why is this a big deal? Well, because they don't shuffle the pack after every time you give a card out. So normally in the casino they would have several packs shuffled together and they would deal cards quite a long way down that combined pack until they stop. And then at some point they would stop and reshuffle all the cards again. So obviously when all the cards have been newly shuffled, the chance of getting an ace is 1 over 13 or 4 over 52. Right? But as you go down the stack of cards, the chance of getting an ace may either go up or go down. So if, for example, you had 4 packs, that would mean in total there are 16 aces. So if in the first 50 cards you already had 10 aces, that would mean there are not too many aces left. Right? A lot of the aces have already come out. So the chance of an ace goes down. On the other hand, if in the first 20 cards or so very few aces came out, then the chance of getting an ace from there onwards would go up, right? Once you've taken a lot of the non-aces out. So the idea behind all these students making money is they keep track of which cards have already been played. Now most people don't have a good enough memory to remember all the cards, but it turns out you essentially need to track at least 3 types of cards. Obviously you need to track the number of aces, Secondly, you need to track the number of cards of value 10, which means Jack, Queen, King. And thirdly, you need to track how many other cards have shown up. So if you can keep track of those three numbers, you can work out what the odds are that you will be able to make blackjack by getting 21. Okay? So these students got very good at keeping track of those three numbers and hence working out when to bet high and when to bet low. Right? So obviously, if you think you're likely to do well, you're going to bet high. When you think you're doing poorly, you're going to bet low. So those two movies were about the US. But what people don't know is there's a similar story about Macau. So Macau now has a whole range of casinos. But in this time, this is the time when Macau was still a Portuguese colony. There was only one casino company. And that casino company was run by a very generous alumni of Hong Kong U, who died recently, Stanley Ho. So Stanley Ho was a very smart gentleman. He knew exactly what he was doing. So these students came to Macau, they were doing card counting, and in those days, playing blackjack in Macau, the particular rules they had about how many packs and how often to deal meant that with card counting you could actually do better than the casino. So in general, the rules in all gambling games and casinos are in favor of the casino. So you normally will lose your money fairly rapidly. But when playing blackjack, if you keep count of the cards, you could get a small advantage against the casino. So these students were doing quite well. They were actually making quite a bit of money against the casino playing blackjack. But Stanley Ho was a very clever gentleman. So what did he do? So he said to the students, you're doing very well against me, right? I'm very impressed. So I wonder whether you would consider giving me a little break to go and get some more money. Why don't I give you the money to go off to Manila for the weekend? You can have a great time in Manila, and then you can come back on Monday and start trying to make money from me again. So the students thought, that sounds like a great idea, right? He's offering to pay for us to go off to Manila for the weekend. We can have a great time in the clubs of Manila for the weekend and come back and play blackjack again on Monday. So what Stanley Ho then did is he went off to talk to the Portuguese governor of Macau and said to him, we need to change the rules for the casino, because he couldn't change the rules himself. He needed the government to approve it. And so the Portuguese governor agreed to the change in the rules. So by the time the students came back on Monday, they were shuffling the pack of cards more frequently. So shuffling the cards more frequently means the advantage you can get from card counting decreased, which meant it was much harder to make money against the casino. Because remember, in general, the casino has much more money than you do, so it's much more likely that you will go broke before they will. So anyway, so this just shows that conditional probability can be very important in some situations. So other than playing cards, where else Bayes' law is used in common life? Well, one other common situation is spam filters. So spam filters are the piece of software inside your email which determines whether email is junk or good emails. So these spam filters look at the probability of an email being good or spam by looking at the probability of it having the characteristics it has if or not it's spam, and then calculating the probability of it being spam given these characteristics. So they update these probabilities as new emails come in. So each time you say to the software, no, this is not spam, this is good, it updates the probability, or the reverse, right? So if you say, no, this is not good, this is spam, then it will update those probabilities. So that's why they're often called Bayesian filters. So you can look it up in Wikipedia. It's called naive Bayes spam filtering. Okay, so Bayes' law actually is useful in other ways as well. It can also be looked at as a way for updating of evidence. So how does that work? So it's particularly easy if we think of where there's only two possible outcomes. So if it's heads or tails or win or lose, we often can think of odds instead of probability. So what are odds? The odds of heads to tails is just the probability of heads divided by the probability of tails. And it turns out that Bayes' law is particularly simple in terms of odds when there are only two possible outcomes. So for example, if we're looking at A or not A given B, the odds of A or not A given B are just the probability of A given B over the probability of not A given B, which is just the probability of A and B divided by the probability of not A and B, because the probability of B terms cancel out. Okay, so in other words, we can use this in a context where we're trying to update our knowledge. So I'm going to show you an example of how we can apply that to evaluate a government policy. So this government policy, so I need to go back a stage. We were talking before about sampling and non-sampling error, right? So let me give you an example of where this was very important. So the government does very large-scale surveys on drug use in schools. Okay, so this is an anonymous survey where they ask students whether or not they are aware of certain drugs and whether or not they have taken certain drugs. Okay, so let's just think about that for a minute. So you are probably all very honest people, and if it was an anonymous survey, you might take that questionnaire very seriously and correctly tell the government which drugs you've heard of and maybe which drugs you've tried. Okay? But I'm sure when you were at school you had some classmates who didn't always take things so seriously and would have fun. So if they had to fill out a questionnaire, they might just fill out a random pattern of boxes on the tick boxes on the form, or they might even be more naughty than that. So if they asked, have you ever taken these drugs, they might say yes to every single drug, just to simply to have fun. They might think it's funny to say, I've taken all of these drugs, even if they haven't. So what's the problem with that? Well, the problem with that is, of course, that means that the information that you got back from those surveys is not just sampling error, but there's non-sampling error due to the fact that some people have not answered the questionnaire seriously. So what that means is, for example, you may not be able to fully trust the results in those questionnaires because you don't know how many of the kids have taken the questionnaire seriously. So what can we do? Well, actually, there is something we can do. So the Hong Kong government has always refused to do this, but if you look at other governments, so the British government or the Taiwanese government, in their drug surveys of school students, they include some questions which enable them to check how serious the non-sampling error is. So how would you do that? Well, what they do is amongst the drugs, when it asks you, have you heard of drug X, they put in a drug that doesn't exist. Right? So if 5% of these students say, I've heard of this drug which we know does not exist, that means that you know that anything below 5% is not to be taken seriously. Because almost certainly these kids are wrong. They're either just wrong because they're ignorant, or they're wrong and intentionally trying to mess up the questionnaire. Similarly, for the question about which drugs have you taken, they also put a different drug in there which doesn't exist. So if 1% of the population says we've taken a drug that doesn't exist, then again, you know the non-sampling error is big enough that you can't trust anything below 1%, as meaning that these kids really have taken drugs. So because the Hong Kong government refused to put these sorts of checks into the questionnaire, they reached the conclusion that in every primary school there were children who have taken drugs. Now, I'm not saying the conclusion is necessarily wrong, But I'm saying that the evidence they presented could not be trusted, because we know some of these kids may not have taken the questionnaire seriously. So the consequence of all of this, and the fact their resistance to using good research methodology, was that they believed that there were a significant number of children taking drugs in Hong Kong schools. Okay, again, I'm not arguing whether the conclusion is correct, but I'm saying it was based on questionable evidence. So they decided they were going to implement drug screening in Hong Kong schools. So there are essentially three straightforward ways to test whether people have been taking drugs. So one is through blood testing, one is through hair samples, and one is through urine testing. So of those three alternatives, blood testing is very invasive, right? You have to stick a needle in somebody. So most people are very unhappy about this and unwilling to give blood samples. Hair samples actually have some advantages, because drugs you've taken show up in your hair samples for quite a long time, but it's relatively expensive to do the chemical analysis of the hair samples. And then the relatively cheap, relatively less invasive option is urine samples. So the government decided to do urine samples of secondary school students. So originally they were going to do it in all secondary school students, but then the Privacy Commissioner pointed out they would need consent from both the children and their parents. So it wasn't enough just to get parental consent, you needed the child's consent as well. So the government decided to trial this in one of the districts. So the question is then, how could you afford to do this? Because actually a very precise urine sample is quite expensive, right? And the government laboratories do not have the capacity to do, tens of thousands of urine sample tests. It would take a lot of time and money. So they decided to do what we call a screening test. So urine, I should point out that urine tests can be very precise, right? There is one form of urine test which is very widely available. Can you think what that is? Maybe you can stop and think for a minute. So actually what it is pregnancy tests. So a pregnancy test is actually a urine test looking for hormones in the blood that indicate that the lady is pregnant. So, but a large amount of money has been invested in making those urine tests very accurate. So the sort of urine tests we're talking about here are not that precise, particularly because we're testing not just for one drug, but usually there is a set of drugs that we're looking for. So we can use these relatively cheap tests. The idea behind this is that when you do a screening test, you're trying to find out who might be a drug user. You can always then do a follow-up test, a more precise one, to check your answers if you get a positive result in the first cycle. Okay, so how does this work? So in other words, you're going to do this relatively cheap test, and if you get any positive results, you then do the second stage, more accurate test. So when the government announced they were going to do this, they asked universities whether they would like to bid on the evaluation of this process. So I turned up to the briefing to talk about the evaluation, and one of the questions I asked as a statistician was, what are the false positive and false negative rates? So what does that mean? That means false positive means what's the chance of a positive result for people who don't have a drug, haven't taken a drug. False negative is what's the chance of a negative result for people who have taken a drug. And the government said, we don't know. And I said, but that's unethical. You shouldn't be doing this without being able to tell people what's the risk that there will be a false positive and false negative. And they said, oh, you don't need to worry. Those are very low. And besides which, we're going to do the second stage of testing. Now, unfortunately, there was a weakness in their process, because their process said we're going to keep anonymity, but they were only focused on the anonymity of the student, not of the school. So if there was a positive result in a school, it was quite clear to me that it might well leak out that there was a positive result in that school, even if nobody knew which child it was. Okay, so that was something of a problem. So the government, it clearly is important. I said to you before that schools get very unhappy if there are children who get arrested and sent to detention centres. Similarly, it would be very damaging to a school's reputation if there were children there who were found to be taking drugs, even if this was only in the first stage of screening. Anyway, so the real question was, how useful is this screening test? So we can use Bayes' law to try and help us work out the odds that someone is a drug user after a positive or a negative screening test. Okay, now there is one slight problem with this framework, is that we need to say something about the odds that they have taken the drug before we do the screening. So in the calculation here, I'm going to assume it's about 1 in 1,000. Right, now that means I'm assuming that for a particular drug, only about 0.1% have taken the drug. So we can change this assumption. We could change it to 1% or 0.01%. We can see what the effect will be on our conclusions. Okay. Now, as I said, I asked them what's the probability of false negatives and false positives. They said they didn't know. I said that was irresponsible. So I went looking for information elsewhere, and I discovered that the Australian government had done the sort of calculations that I'm going to show you, and they had insisted on being told the false positive and negative rates, and they found out that it was about 2%. Right? So amongst the kids who've taken the drug, about 2% of them would not be picked up by the test, and amongst the ones who haven't taken the drug, there was about a 2% chance that the test would say they might have taken the drug. Okay, so we can write this all down then. So as I said, I'm assuming the probability of D for drug over not D, meaning not drug, is about 1 in 1,000. So that's 10 to the minus 3. The probability of a positive screen, S, given I've taken a drug, we said is 98%. And similarly, the probability of not S, a negative screen given I've taken a drug, is 2%. Similarly, the probability of positive screen if I've not taken a drug is 2%. And a negative screen if I've not taken a drug is 98%. So if we put those things together, what we really want to know is the odds of taking the drug with a positive screen and the odds of taking the drug with a negative screen. So we can write those down as the probability of D given S over the probability of not D given S, and the probability of D given not S over the probability of not D given not S. So using Bayes' law, we have the probability of D given S is the probability of S given D over the probability of D divided by the probability of S, and similarly the probability of not D given S is probability of S given not D times the probability of not D over the probability of S. In other words, the probability of D given S over the probability of not D given S, which is the odds of taking the drug with a positive screen after collecting our information, in other words, which we call the posterior odds, means the odds after collecting the information, is the probability of S given D over the probability of S given not D times the probability of D over the probability of not D. So the probability of D over the probability of not D is what we call the prior odds, meaning the odds of being a drug user before we get this information. And then the bit in between is what we call in statistics a likelihood ratio. So this is the probability of a positive screen under the two situations where either the person's a drug user or not a drug user. So that likelihood ratio is 98% divided by 2%. So that says a positive screen increases the odds by a ratio of about 50. Right? So if we start out with 0.1%, we end up with about 5% is the odds ratio, or if you like, 1 in 20. Similarly, if we have a negative screen, that makes the odds 50 times less likely. So instead of 1 in 1,000, it becomes 1 in 50,000. So let's think about that for a minute. So that's saying if I choose a student at random, and if they give a positive screen, I still only expect about a 1 in 20 chance that they actually are a drug user. Okay? If I get a negative screen, it's extremely unlikely they're a drug user, right? It's 1 in 50,000. So I think I worked out the cohort size is about 400,000. So amongst the ones with negative screen, there would be very few kids who are drug users. So is it a useful screen? Well, the problem, of course, is that, as I said, this is saying even with a positive screen, it's still only 1 in 20 chance that they actually have taken the drug. So we definitely need the second stage. So if it became leaked that there was a positive screen, actually we cannot conclude that there are any kids in that school who took drugs. Right? That would just tell us there is a chance that one of them has taken drugs. Okay, now you might say, okay, the 0.1% rate I assume to start with is too low. So what if we said it's 1%? So if we started out with 1% instead of 0.1%, that would mean that the odds ratio is about 1 to 1. Right? So that would make it, so that would make the odds ratio 1 in 2 instead of 1 in 20. So it would still only be a 50-50 chance that a kid was a drug user if the overall rate is 1% and I get a positive screen. So this is really quite scary, right? It's potentially seriously damaging to the school if we got a positive result. So, if we want to consider whether it's a useful screen, actually there is a lot more we need to consider than just these two odds. We need to consider the costs of wrong decisions and the cost of data collection. But what we're saying is at the individual level, this is not very useful. We would still have to go and do the second stage screen if we, on all the cases where we get a positive result. Because even if the prevalence rate is 1%, we would still only have a 50-50 chance that that particular child is a drug user. Now, I mentioned before that kids have to give consent as well as the parents. What I didn't mention was how well this screening works. So one of the things about urine is that the idea is if you've taken a drug, it's not that you pass out the drug itself, but you pass out some byproduct from your stomach processing and your kidneys processing the drug. So you could reasonably ask the question, after how long can you detect it? Well, it turns out it works for 2 or 3 days for most drugs. So after 2 or 3 days, there is so little of the drug left in your body that it's not possible to detect it using the screening tool anyway. So we're assuming you've done this basically within 24 hours in order to get these results. Now, if you know something about Hong Kong, and I think the mainland is similar, on weekday nights, most school-aged children are busy at home doing homework. I'm not sure how the virus has affected this, but normally you would come home from school, you would either go to tutorial school or you would come home and start doing your homework and be doing homework until it's nearly time to go to bed. So most kids can't go out on school nights in Hong Kong. They're too busy doing homework. So in order to take drugs, and in fact, for teenagers, the most common drug in the past was ketamine. And in most cases, these kids would go across the border to Shenzhen into a club in order to take ketamine. It was too hard to get the drug in Hong Kong. It's much easier to go across the border. So usually kids could only do this on a weekend, right? So probably a Friday or Saturday night, probably Sunday night, the kids make them come in. Parents make the kids come in early and go to bed so they can get up in the morning to go to school on Monday. So if they went out on a Friday or a Saturday night, probably they would need to be tested on a Monday in order to detect them taking the drug. Tuesday onwards, probably the level in their body has gone down enough it wouldn't be detectable. And then also you've got this element that kids had to consent to being tested. So you think about it for a minute. Let's say you have gone out on Friday or Saturday night. You did take some drugs, whether it's ketamine or marijuana or ecstasy, whatever it was. And on Monday morning, you go into school and the teacher says, you have been selected to be randomly tested for drugs. Do you consent to this? You think about it. Are you going to say yes? So the government's argument was that these kids need help, they just don't want to ask for help. But I'm afraid I don't think I see it that way. All the young people I've met, most of them, if I was being asked whether I were willing to be tested on Monday morning, I would say, sorry, no, I'm not feeling well, or I don't feel in the mood, or I don't want to be tested, if I knew that I might be detected as having taken drugs over the previous few nights. Anyway, the government spent a lot of money testing tens of thousands of students. Right? So given all I've said, how many positive screening results do you think they got? I think they did this for 3 years. How many do you think they got? So you can't see my hands. So normally in the classroom, I would put up my fingers to tell you that the answer is 0. In other words, they did not detect a single child taking drugs in that district over a 2 or 3 year period. Now, I don't frankly believe that there are no kids taking drugs. That doesn't sound believable to me. So I'm sure that leads to the reasonable conclusion that the kids who had been taking drugs, either it was long enough since they took the drugs that couldn't be detected, or they refused to be tested. Right? So you can draw your own conclusions. But I would argue that if the government had, like the Australian government, done a Bayesian analysis like this to work out the benefit of doing the screening test, I think they would have concluded this was not a very good way of spending the money, because they spent a lot of money, I think millions of dollars doing this testing. So I'm not saying that testing is of no value, but testing in the population like this is what I would say is probably not of value. So my children went to an international school in Hong Kong, and in fact, that international school does have a drug testing policy, but a very different drug testing policy. And that's a drug testing policy that the parents and the children must consent to in order to attend that school. So because they're not a government school, they can make it conditional. And what they said was, if any teacher has reason to believe that a student has been taking drugs, right, their behavior in the classroom, whether they're falling asleep in a situation where they shouldn't be, or they're behaving strangely in a way that makes the teacher believe they may have taken drugs, they can be given a drug test. Okay? And indeed, they did find some kids who had taken drugs as a result of that policy. They didn't automatically throw them out. They generally at least required them to go through counseling and address the issues. If they had passed on drugs to anyone else, they would definitely get thrown out. But it was definitely an intervention in those situations. So a very different policy. Right? It was focused on helping the children rather than trying to estimate how many kids had taken drugs. In a situation where, as I explained, this probably wasn't a very valuable approach. So, as I said, the government defended their position on the basis that all positive would be double-checked, but the testing scheme operators would all know that a student tests positive, which could easily be leaked to the media. Okay, so that's the end of chapter 6.